In 2017, astronomers made a stunning astronomical discovery. They found an ultra-cool red dwarf star, TRAPPIST-1, with 7 Earth-sized planets orbiting it. That's the most number of planets we've ever found orbiting a star other than the Sun. This discovery was significant for 3 reasons. Firstly, the planetary system was relatively close, located just 40 light-years away. Secondly, all 7 planets were rocky, like the inner planets in our solar system. Lastly, 3 of the planets were in the habitable zone, making them promising targets for finding extraterrestrial life. The discovery ignited enthusiasm among astronomers, and advanced telescopes, such as the Hubble Space Telescope, were utilized to study the remarkable planetary system. However, these telescopes had limitations, and their findings were capped due to wavelength restrictions. As a result, astronomers eagerly awaited the launch of the James Webb Space Telescope to focus on the TRAPPIST-1 system. And now, the first results from the telescope have been received, but they are not promising. So what did Webb discover in one of the planets of the system? What techniques were used to determine the nature of the planet orbiting TRAPPIST-1? Finally, and most importantly, why are these results so critical for astronomers? To fully comprehend the significance of Webb's findings on TRAPPIST-1b, it is important to consider the nature of the host star. TRAPPIST-1 is an M-dwarf or an ultra-cool red dwarf star. M-dwarfs are the most common type of stars in our galaxy, accounting for about 75% of all stars. They are smaller and cooler than the Sun, with surface temperatures ranging between 2400 and 3800 Kelvin, and masses ranging from 0.08 to 0.6 solar masses. TRAPPIST-1, for instance, is just 9% of the Sun's mass, but it is 2.5 billion years older than the Sun. While M-dwarfs are twice as likely as Sun-like stars to host rocky planets, they present a significant challenge to planetary habitability. This is because M-dwarf stars are highly active, producing frequent flares and coronal mass ejections that release large amounts of energy and charged particles into space. These events can have a profound impact on any nearby planet. The intense radiation and energetic particles emitted by M-dwarf stars can strip away a planet's atmosphere and erode its surface, a process known as atmospheric escape. This can be especially destructive to planets that orbit close to the star. In the case of the TRAPPIST-1 system, this issue is worsened by the tightly packed orbits of all 7 planets. These orbits are so close that they could all fit inside the orbit of Mercury in our solar system. The closest planet, TRAPPIST-1b, orbits the star once every 36 hours and receives about 4 times more radiation per unit of surface area than Earth does from the Sun. Despite all these factors, this is the planet that astronomers chose to observe with the James Webb Space Telescope. One of the most intriguing questions in astronomy is how scientists are able to determine the properties of planets located trillions of miles away from Earth. The answer lies in spectroscopy, a branch of physics that revolutionized astronomy more than a century ago. Specifically, astronomers rely on the concept of secondary eclipses to gain insight into the temperature and composition of these distant worlds. When a planet passes in front of its star, as seen from Earth, it blocks a small fraction of the starlight. By analyzing the dip in the light curve of the star, scientists can infer the presence and orbit of an exoplanet. However, this configuration only provides information about the planet's night side facing us. To gain a complete understanding of the planet's atmosphere, scientists rely on 2 additional configurations: when the planet is on either side of its star, or when it's behind the star, as seen from Earth. But why is the latter configuration so critical when we can't even see the planet? The answer is the infrared emission from the exoplanet. TRAPPIST-1b is tidally locked, meaning that one side always faces the star while the other is in permanent darkness. If the planet has an atmosphere to circulate and redistribute heat, the day side will be cooler than if there is no atmosphere. Although TRAPPIST-1b is not hot enough to give off visible light, it does have an infrared glow. When the planet passes in front of or on either side of the star, the resulting light emitted is a combination of the light reflected from the star and the planet's own infrared thermal emission. Hence, the system appears brighter. However, during a secondary eclipse, no infrared emission is recorded from the planet because it is not even in the scene. So by subtracting the star's brightness on its own during the secondary eclipse from the brightness of the star and planet combined, they successfully calculated how much infrared light the planet was giving off. The researchers were able to observe 5 secondary eclipses for TRAPPIST-1b, a significant milestone in itself, given that the star is over 1,000 times brighter than the planet. The change in brightness detected by Webb is less than 0.1%. The results are based on measurements made by Webb's Mid-Infrared Instrument, or MIRI, which detected an infrared glow from the planet's day side, indicating a temperature of approximately 230 degrees Celsius, suggesting that TRAPPIST-1b is a rocky, barren planet with no significant atmosphere. Previous observations using the Hubble and Spitzer space telescopes found no evidence of a puffy atmosphere, but could not rule out a denser one. In contrast, Webb's results are almost perfectly consistent, with a black body made of bare rock and no atmosphere to circulate the heat. In addition, there were no signs of light being absorbed by carbon dioxide, which would be apparent in these measurements. The groundbreaking research represents the first detection of any form of light emitted by an exoplanet as small and cool as the rocky planets in our own solar system. It is a significant step forward in our quest to determine whether planets orbiting small active stars like TRAPPIST-1 can sustain the atmospheres needed to support life. Furthermore, it highlights the capabilities of Webb and its mid-infrared instrument in characterizing temperate, Earth-sized exoplanets. This research was conducted as part of Webb Guaranteed Time Observation Program 1177, one of 8 programs from Webb's first year of science designed to help fully characterize the TRAPPIST-1 system. NASA says additional secondary eclipse observations of TRAPPIST-1b are currently underway, with the team hoping to eventually capture a full phase curve showing the change in brightness over the planet's entire orbit. This will enable them to gain further insights into the planet's temperature and other key details. Recently, astronomers found the first ever dark galaxy that emits no visible light. This could solve one of the biggest problems in astronomy: the missing satellite problem. If you missed this episode, be sure to catch up on this exciting discovery.